Okay. First of all, thanks to organizers for the invitation. So I'm going to talk about this recent work with students Yuzhen Zhang and Wenwen Zheng, both grad students at Santa Barbara. Recent progress in de Sitter space suggests that conditioning on the existence of observer, the de Sitter horizon may be described by quantum mechanics. The evidences approaches include the use of a von Neumann algebra, the phase of the Safier-Pachin function, other potential microscopic models, TT bar deformation, time-like Liouville theory. We've heard basically most of them in this week. My understanding of this idea is that there's a conjecture static patch Hilbert space that is the union of the observer Hilbert space and a microscopic de Sitter Hilbert space, subject to the Hamiltonian constraint. In this context, the Safier-Pachin function calculates the trace of the Hilbert space. We would like to test this idea using random matrix universality. The random matrix universality is a conjecture that the spectra of a chaotic system should have the same fluctuation properties as predicted by random matrix theory. So in the GOE context, one can study the spectral form factor and should exhibit the ramp Plateau structure, where the ramp mainly comes from the spectral rigidity of the spectral density. In the gravity context, the presence of horizons in both the de Sitter and black hole space indicates the underlying microscopic system should be chaotic, and therefore we expect it should satisfy random matrix universality. In fact, Saad, Shenker, Stanford already discovered that for geometries with a Killing horizon, one can construct a universal wormhole called the double cone. Such a wormhole is constructed by doing a periodic identification of the eternal Pan's diagram. And that works for both the black hole and de Sitter space. There will be a singularity at the bifurcation center, and that requires particular I epsilon description that I will discuss later. But the main basic result is that in the black hole context, there exists a family of thermal field double states that labeled by the relative time shift between the two asymptotic boundaries, and trace over those thermal field double states lead to a ramp. In the de Sitter context, Chandler, Shenker, Logan, Pennington, Wheaton showed in their paper that if you consider the physical Hilbert space of two identical observers on the two-stat patch, then the thermal field, the Hilbert space also contains this L2 of R, and it's R minus because they impose an energy constraint that describe the relative time shift between the two clocks of the observers. This should also lead to a ramp. The goal of the talk is to try to provide an explicit calculation of this expectation using gravitational path integral. So here I draw two circles. On the left-hand side, the circle represents the asymptotic boundary conditions of anti-de Sitter space. And the right circle represents some condition on the observer which form a closed loop. The rule of a gravitational path integral we'll use is that in anti-de Sitter space, we sum over all geometries compatible with the asymptotic boundary condition. And in de Sitter space, we sum over all closed manifolds conditioning on the behavior of the observer. In particular, for the context of the double cone, we want to perform a summation over all geometries that can contain two observers whose clock winds from 0 to t and 0 to minus t. So it can contain sphere with two observers, or disconnected geometries, two disconnected spheres with two observers, with observers on each of the sphere, or you put two observers on the double cone. The interpretation of this calculation is that this calculates the return probability of the microscopic system under the evolution of the clock H observer. This quantity is related to this late time behavior of a static patch correlator, as discussed in the last talk. We will find, and we will argue actually, the final result of the Euclidean path integral on the double cone wormhole give you a linear ramp for time bigger than the de Sitter-Hubble time. And therefore, it obeys the BGS conjecture. And in particular, the time scale where this return probability approach to a linear ramp in the random matrix theory usually defined as the Thoros time. And here we find the Thoros time equal to the de Sitter-Hubble time. Okay. So that's an overview of the result. The calculation, the theory will consider contain three actions. The first is the Einstein-Hilbert action of with positive cosmological constant in d dimension, and then we use this observer action that was use the notation in Huan's sphere path integral paper that contains relativistic particle union a free clock. So for this observer action, the first term describes the relative motion of the observer in the spacetime. And this curly T and curly E denotes the clock time and energy that's supposed to measure the observer's proper time. And in addition, you can put any other matter field in de Sitter space. We will first discuss this quantization of this observer particle, observer action. So let's consider the propagator of this observer model, the Euclidean propagator of this observer model, say from a location x0 to x1, and the clock runs from 0 to t. That involves the following path integral. The x of lambda is a map from the interval to a Euclidean de Sitter space, which, for example, is SD. And that parameterizes this particle's trajectory by lambda. And also, we have this clock path. Here, we consider it to be a monotonic map from 0, 1 to 0, t. And this system have a gauge symmetry, which is a reparametrization around the wall line of the observer that takes this form. To quantize this system, we can first gauge fix the reparametrization symmetry by fixing the clock path to be linearly in lambda. And that allows then the integral of the energy of the clock just impose the that function constraint that the total proper time of the observer should be t. That reduces this path integral of this observer model into a simple sum of all passes with fixed proper length on the sphere. So at microscopic level, this path integral is nothing but Brownian motion of a sum of fixed paths, which have which is a fractal and has Hausdorff dimension 2. And in the continuous limit, this path integral flows to the standard nonlinear sigma model mapped from interval to SD. Mu is a continuous mass parameter. This is analog to the hydrodynamics approach to the black hole thermodynamics, where we have a physical spacetime, which is a asymptotic boundary, and maps to the bulk fluid spacetime, for example, in the ADS space. In our case, because we just have consider the simplest ingredient where we have a word line and the clock. The clock time plays a role of physical time, while the Euclidean sphere, SD, or its another continuation to de Sitter, serves as a fluid spacetime. That's a target spacetime of this nonlinear signal model. Classically, you can understand this statement because if you consider a relativity particle in d-dimensional space, it has a degree freedom given by the spatial location. But then we add the clock that just adds the degree freedom in the time direction, and that matches the degree freedom of this nonlinear signal model. And we'll use this nonlinear signal model to calculate the double cone partitioning function. But before we move on, let me make a comment on the two-sided Hilbert space in eternal de Sitter space to make context with CLPW. In a two-sided de Sitter space, we necessarily need two such particles. And in addition, we need to impose we need to gauge the de Sitter isometry. And classically, you can fix the de Sitter isometry by first setting one of the particle on the at t equal to 0 at the north pole of the spatial sphere. And this gauge fixing condition will have a residual isometry that's SOD minus 1, 1. And you can use this residual isometry to fix the location of the right particle up to the relative time shift t. And that means the physical Hilbert space of this two-sided observers reduces to the L2 of R. That's just described by the relative time shift. And this can be formalized using the co-invariant Hilbert space approach, and one can verify it gives you this L2 of R plus. Now let's consider the double cone partitioning function. Just to recap, Saad, Shenker, Stanford construct this double cone to be a universal complexified on-shell solutions of Einstein gravity that is associated with geometries with Killing horizon. You obtain this wormhole geometry by taking a finite quotient with respect to the Booth symmetry of the system, and that leads to a singularity at the horizon. Then to resolve the singularity, you go you do another continuation of the radial coordinate. Here it is a theta around into the imaginary plane. So explicitly, the metric of the de Sitter double cone is given by the following metric. And you should think understanding this as the on-shell geometry in the limit epsilon go to 0. And the whole manifold is smooth in this limit. So from the construction I described, it's manifest that it's universal for any Killing horizons. And so this I epsilon deformation only requires a near horizon radial structure. And that's the reason why it applies to both the black hole and de Sitter horizon. And due to the analytic continuation of the radial coordinates, the metric remains smooth. And any physical quantities you can calculate from this double cone geometry are independent of the specific value of epsilon. In the de Sitter, this double cone will contain two closed time-like geodesics at the pole and the antipode. That means two stat patches. And classically, that can support the observers to live in. And that contributes as a connected geometry to the return probability I defined before. If you calculate the on-shell action of the Einstein-Hilbert action, then you find the action vanishes because the volume of the double cone actually vanishes due to the another continuation. That means it's exponentially suppressed relative to the sphere partitioning function. that also means the calculation of the path integral reduced to the calculation of the one-loop determinants around the double cone geometry. And in particular, we'll consider the one-loop determinant of the matter and the observer. How many time do I have? 20 minutes, okay. So let's first discuss the matter patching function. Because of the construction of the double cone, one can understand the matter patching function as evaluating a bulk trace with a modified boost evolution operator that was pointed out by a paper by Chen, Ivo, Madasena. Here, this modified boost operator is a difference between the ordinary boost operator that generates a stat patch and the local Minkowski Hamiltonian defined near the bifurcation horizon. And this I epsilon description comes from the I epsilon description of the Saad, Shenker, Stanford. And the spectrum of this modified boost operator turns out to be given by the quasi-normal frequency of the system. And so one can directly write down the final result in terms of the sum of the quasi-normal modes. And in particular, this quantity will decay to 1 for time bigger than the de Sitter Hubble time. And that defines what I call the Thoros time. And that's given by the Hubble time. Now let's go to the observer part. At a big level, we can also think about the observer patching function as calculating the bulk trace of the observer Hilbert space. But now, that observer Hilbert space is the one that I described, this L2 of R. But now, this observer Hilbert space is invariant under any de Sitter isometries. Therefore, you seemingly get just a trace of the total Hilbert space dimension of the observer. That is classically is an integral over the energy and time of the phase space integral, and it diverges. But now, on the double cone, the relative time shift is compactified to the range of the double cone period, capital T. And therefore, we expected this observer patching function just going to be truncated to the T integral will be compactified to be proportional to the range of the double cone, period of the double cone. And moreover, when the observer is heavy, we expected the period of the double cone should be locked to the clock time T. And that is the big argument why the observer patching function should give you a linear in T ramp. And this delta E is just to describe the total energy window you consider. But that's not very rigorous, especially this compactification is kind of hand-waving. It will be nice to have a very more formal construction of this type of argument, but I don't have it right now. So instead, we try to directly calculating the path integral, calculating this patching function using Euclidean path integral. So we were calculating the nonlinear sigma model on this double cone with fixed periodicity T. In the large mass limit, one can just do one loop calculation, and they fix it, and the result with fixing periodicities of the left and right clock is the following. Here, curly T left represent the amount of clock evolution on the left observer. T right is the right observer, and this capital T is the period of the double cone that we take in quotient. Let me explain this result. The classical saddle, which is this piece, is given by these two observers sitting at both sides of the double cone. And that, the classical action gives you this, this linear in T squared piece. And then you have this 1 over square root of the T left, T right piece that comes from the fluctuations of the time direction, the time mode of the observer. And this linear in t corresponding to the zero mode integral, where you have a relative time shift between the t equal to 0 between these two observers. But you also have this 1/sinh t factor that comes from the transverse fluctuations of these two particles. Basically, when the particle is very heavy, you expected the particle to display the same quasi-normal mode decay as for the matter partition function, and that's captured by this 1/sinh t factor. And that's also related to Douglas' comment to Murada's talk in an hour ago. One should compare this result with the double trumpet partition function in JT gravity, where we can fix the period, the geodesic of the double trumpet to be B, and then the double trumpet partition function take this form. So you can identify beta with this curly T, and B with the periodicity of the double cone after another continuation. And the only additional factor is this 1/sinh t factor. So to make comparison with this double trumpet partition function, I already make manifest that to calculating the full return probability, we have to sum over the double cone geometries. So that's we can do. We want to integrating over t, but then we also have an undetermined measure factor that I call mu of t here. Right, in terms of this formula, it's kind of clear that what I'm going to do is to make this mu of t to cancel with 1/sinh t factor. But we need the argument why this cancel each other. So the argument we gave in our paper is the following. If we consider the construction of the double cone, it's kind of clear that we can take a quotient with any group element in the SOD, 1 that is conjugate to the boost. Both quotient give you a smooth double cone construction. But the reason that we only consider the quotient of the boost associated with the static patch is that this different group element quotient are related by G. So in other words, a proper way to describe the double cone is that the double cone we constructed, it's associated with the conjugacy class in the SOD, 1. And the integration measure of a conjugacy class can be naturally induced from the Hall measure of the original group via the wire integration formula. If you assume you're starting with the Hall measure. And that's the result you can calculate using the wire integration formula associated with this SOD, 1. So the measure associated with this conjugacy class of the boost evolution operator exactly give you this sinh t factor with the right little d. Sorry, little d is the spatial dimension. And these two cancel perfectly. And if you assume to use this measure, then you get the familiar result. And after going to the microcanonical ensemble, you recover the ramp result. But I should stress that it's essentially an assumption that we start with the Hall measure of the group G. In principle, to determine this measure, I think one need to start with archeolocal measure of high-dimensional gravity and to reduce to the measures of integration of the double cone. But I don't see immediately how to do that. I should also comment that even for high-dimensional black holes, you have similar issue. Another comment. Actually, no. You ask me during the discussion. The final result we get is that the double cone contribute to a linear ramp growth for the return probability. And what is the microscopic origin of this double cone? If we believe this, the de Sitter static patch admits a quantum mechanical description, then we can use this picture of this microscopic Hilbert space, where we have the Hilbert space of de Sitter and observer subject to the Hamiltonian constraint. Then you can evaluate the return probability as evaluating the spectral form factor of the H de Sitter. Here, E and the rho of E are the energy and the spectral density of the de Sitter Hamiltonian. And then you can associate the linear ramp with the spectral rigidity of the H de Sitter. Let me make some comments of other double cone geometries in this game. In de Sitter closed manifold, you can construct a larger family of double cone wormholes starting from de Sitter black hole geometries. In this case, because you have both the horizon of the black hole and the cosmic horizons, and the gluing gives you a topology of a T2 cross S2. But once you put an observer in such geometry, such contribution decays at late time. This is because the black hole will break your group, the isometry group, to the one of the static patch, and then the measure is just equal to 1. So you will suffer this exponential decay we were discussing before. And one can understand this decay as a quasi-normal mode decay of the black hole. In particular, if you think about the black hole is very small, you can treat it as an ordinary matter excitation in the static patch, and that will decay exponentially as a massive particle. One can also consider the black hole as observer instead of putting additional word line on this geometry. Then, if you don't couple to any matter field, including graviton, then one can also get a ramp, just becomes comes from the twist mode of the torus, of the base torus. But if you consider matter field, there will be no such linear ramp. That's because in the black hole and de Sitter now will be coupled together. And if you evolve with the de Sitter mass, that will not give you any ramp. And in other words, the evolution of the de Sitter Hamiltonian seems to be a bad probe of this spectral statistics. There are also other geometries. For example, in pure de Sitter, one can construct other conjugacy classes in the SOD, 1. Those, I think, corresponding to turn-on angular velocities of the spatial sphere. And if we enrich our observer model by, for example, carry a rotor that is rotating in the spatial directions, one can, it could be sensitive to those conjugacy classes. And one can also gauge a time reversal symmetry, and maybe it's necessary to gauge the time reversal symmetry. That will introduce an additional factor of 2 in this game. Okay, so we argue that in the presence of observer, there are non-perturbative correction to the return probability using Euclidean path integral. And that seems consistent with the assumption that static patch de Sitter space have a microscopic Hamiltonian satisfy random matrix universality.
Yeah, so 2 questions. One is please make the comment that you missed before.
Okay.
And the second is also ask for comments, is that you mentioned that this H de Sitter looks like a standard Hamiltonian system. But how about, do you have any thoughts or comments about this time advance?
Okay. Okay, but before making my first comment, I want to also make an advertisement that next year we'll have a workshop on random geometries at Stony Brook. It's about making connection with this Liouville, the Liouville field theory in the math literature and the recent development in JT gravities. And there's a long program from March to May, and then there's a workshop. And also, we have a quantum information, quantum gravity, this QIQG meeting in Beijing the week before strings. So I welcome all of you to participate. Now, for the first comment is to make connection. First of all, to make the first comment, some of you may thinking about this. We didn't see this cinch factor in the usual JT case, and why that? And I think it's because in the standard case in ADS2, we use a symplectic measure of the Schwarzschild particle, and on the trumpet it takes this form. But in our analysis, it's more natural to use an ultralocal measure of this boundary of the observer, and that's like using the ultralocal measure of the Schwarzschild particle. And if you use the ultralocal measure of the Schwarzschild particle, you also find this cinch factor, and that makes sense because you can think about this Schwarzschild particle as a particle with a magnetic field moving in ADS. And if you put it on take a quotient with a boost, this particle magnetic field will also display quasi-normal mode decay. And now because it have large magnetic field, it just have this kind of the quasi-normal mode will have an imaginary part, which is 1/2. And that's the reason why the ultralocal measure of the Schwarzschild particle also have this cinch factor. But in that case, we have a UV defined measure. So for example, you can use the BF theory to derive the actual measure for the Schwarzschild particle, and that gives you this additional factor, roughly is the same as this wide integration formula. And that's how it cancels in the JT case. So I'm not aware of similar analysis was done for higher dimensional black holes. Okay. Even though we expected this ramp, also the double cone also contribute for higher dimensional black holes. Okay, now to talk about the minor signs, the time advance. Is that I'm not sure whether that's really an issue or not. The time advancing seems to be an issue if we try to interpret the two-sided de Sitter space as an entangled state. But from a single stat patch observer point of view, I'm not sure there is a sharp contradiction.
Yeah, maybe I missed what you said about the black hole case. So you say in the when you put the black hole, somehow you don't get the spectral form factor, the correct spectral form factor. What is the physical interpretation of that?
You mean if you treat the black hole as an observer?
Yeah.
Okay. So first of all, why you don't get the ramp? So here, this ramp really coming from thermophile double state, or the like in the semi-classical picture coming from some thermophile double state. But if you put a black hole with a matter, you only have a single Hartle-Hawking state of the okay. Yeah, let's use Hartle-Hawking state. So to replace the word of thermophile double state. If you in a black hole background, when you put matter field, you only have a single Hartle-Hawking state. So if you're trying to like make a relative boost between the black hole around the black hole horizon, that will not be boost invariant.
Is this arising because the two black holes are connected through the interiors?
You mean the twist mode?
The fact that you don't have the twist.
Yeah, because black hole and de Sitter are connected. It's similar as when you have two black holes that couple together, you yeah, you don't have this ramp if you're just evolving one of the energy of the black hole. And
asking about
the conceptual. Oh yeah, okay, yeah, that's where I'm coming. So here you're thinking about the underlying microscopic system satisfy the Hamiltonian constraint that the clock energy and the H de Sitter, they are not coupled together. And then if we evolve with this curly E, that probes the spectral statistics of H de Sitter. But now if you consider they are coupled together, then the evolution of E will not be equal to the H de Sitter, the spectral statistics of the H de Sitter.
So you're saying the double complexity for the black hole case is just the back. You should use some other probe.
Yes.
But system should still be chaotic. Just you have to use some other probe.
Yes. I think it just this is not good probe if your black hole coupled to the Sitter.
Can you comment a bit to the relation to the talk that we heard, the last talk Mehrdad's talk? If you were to insert some operators along the world line of the observer to measure a two-point function, would you recover the same geometry? So instead of computing just the trace, suppose that you computed a trace with two operator insertion, would that be the same geometry as the one that's drawn right behind you? Kind of analytic continuation of that job.
Like this, Mehrdad's talk, he put these two, my understanding, he put these two observers on a sphere. And so you may worry about this one loop determinants. Okay. Now you can think about putting these two observers on this double cone type of geometry, inserting operators. Then it seems that, so naively, you first of all, when you do the calculation, I think you also get this one loop decaying piece that I was talking about. But there, I think, but from this co-invariant Hilbert space type of this canonical quantized Hilbert space point of view, there's no way these two observers can like move because they only have this L2 of R. And if these two particles connected through each other, that's going back to this L2 of R, this the Hilbert space of two observers. And that's related to Dogger's comment that in the ADS case, this because of the SL2 constraint, these two observers had to be locked together. And so you expect it in this case, at least for this calculation of this fluctuation of even like 1-point function squared or 2-point function squared, that calculating the spectral statistics of the OPEs of the 1-point function, that should also exist. But so far, no explicit calculation has been done.
You assume that the observer in this discussion is eternal. So do you have comments on this area where the observer could be annihilated and re-emerge because of the coupling to some matter field in the theta?
No.
Maybe this may be related to the time advance question. So if I consider some matter, is there some way to generalize this, like by adding in some background matter?
Yeah, we consider adding matter in this background, and those have this polynomial mode decay.
So is this matter falling behind the horizon?
Yes.
I was getting confused about HDS. Is this a one-sided or two-sided?
One-sided.
But then the Hamiltonian constraint is, you're saying it's a one-sided still?
Yes. So you're thinking about you have observer and it with some. This was invented by Flex. So. So you have a single observer, and then you have a stretch horizon. You have a HDC, and the whole thing is a closed universe, a closed manifold.
You said that the physical results are independent of the value of epsilon in the regulator. Do you mean that they're actually independent of finite value, or they're just well defined in the limit?
Independent of the actual value.
Oh, why is that?
So, any physical result you're going to calculate will be something like the integral over the radial direction of the theta around the contour you are choosing, and there's an analytic function, and the integral of analytic function that depends on the contour.
I see.
I guess for the pole and antipode cycle on double cone, it's uncontractable cycle. And can the clock cycle have some more winding mode?
Yes. Yeah, you can have multiple windings so even for when you consider the one loop calculation, you can have classical saddles with observer winding multiple times around the at the pole and antipode, and those also decays exponentially. That's because you can think about the exponential decay as describing the relative motions of the observer. So when you have two windings, for example, you're thinking about it's one observer, you have two observers in the incident static patch. And then with respect to one observer, another observer will just decay into the incident horizon. And that's so that polynomial decay agrees with this this calculation when you put two windings.
And the measure factor is the same?
No. So in that case, because the particle now went twice, so you have this. So instead of sinh t for n winding, it's sinh n times t, and yeah, so you have this e to the -1 times t decay.
It looks like the